part 3 of chapter 3, we're going to look at the random walk model, continuing from slide 24. So the random walk model is a very simple model. Here it is in M5. Yn is yn minus 1 plus epsilon n, where epsilon n is white noise. And despite being such a simple model, it's also quite a useful model. Now, as we already mentioned, a difference equation needs initial values to complete the specification. We usually initialize with y0 is 0, so we start the random walk at 0. If epsilon n is Gaussian white noise, we have a Gaussian random walk. This is a special case of the AR1 with an AR coefficient phi1 equals 1. And there's an exact solution if you have initial value y0 is 0, then yn is just the sum of the epsilon k's from k is 1 to n. So it's a cumulative sum of a random walk. One thing that you can get from this is the variance of yn. The variance of yn, it's a sum of independent things, so the variance is n sigma squared, where sigma squared is the variance of any epsilon. And in particular, this shows that yn is not stationary. Right, so the white noise is stationary, but when we sum it up, we get something that's not stationary. It's mean stationary, it always has mean 0, but it's not fully stationary. White noise can also be called, random walk can also be called integrated white noise. That follows the thought pattern that summation is a discrete version of integration. If the data are modeled as a random walk, the value of y0 is usually not known. And rather than introducing an unknown parameter to our model, we may initialize our model at time t1 with y1 equals just the data point y1 star. And that simplifies matters. That's rather equivalent to studying the difference time series. So if we take the first difference time series, call it Z, then Zn is yn minus 1. If we, we only have data from 1 to n, so we have a time series length n, we only get n minus 1 first differences. And that's kind of rather equivalent to being unable to talk about where the random walk starts. You only talk about the increments of the random walk. One thing we can do with a random walk, we can add some drift, and this is also a useful time series model. Here it is in M6. Yn is yn minus 1 plus mu plus epsilon n, where epsilon n is white noise. This also has an explicit solution. Yn is y0 plus n mu plus the sum of the epsilon k's, assuming we initialize at 0 at y, so we set y0 to be 0. When you write a random walk with drift, it's usual to use mu for this drift parameter. But here, mu is the mean of the increments rather than the mean of the random walk process itself, which is a kind of conflict of notation, but that's how it is. You just have to look out for it. Right, so implicitly we have initialized here with y0 is 0. Well, no, okay. So when I wrote this equation, I wrote it in terms of y0, but often we set y0 equals 0 in this equation, and then just yn is n mu plus the sum of the white noises. One situation where the random walk model is a fairly famous model is in the context of modeling financial markets. And here we've already hinted at this before. The theory of efficient financial markets suggests that the logarithm of the stock market index might behave like a random walk with drift. And that's again equivalent to saying that the difference of the logarithms, which is the return, is white noise. Okay, so let's look at some data to investigate this. Here I got some data downloaded from Yahoo. It's the S&P 500 index over a certain time interval. And this is, here we're just plotting the data. The data's on the left at the bottom. Whenever you have data of financial objects, it's very commonly a good idea to take the log. The log is the thing that we think might look like the random walk with drift. Here is the log on the right-hand side, and it does indeed have some drift that might look roughly linear. It would have been better to plot the actual time on this plot. Let's actually write here. So we're going to, and that's just a little plotting dates on time plots is just a little technical exercise. Really, here we're demonstrating that it's annoying when you don't have them on. But I'm going to tell you here that from my recollection, the data are 1950 odd through 2016, and so there's roughly linear growth in the log of the S&P 500, but a certain amount of variation, and we might be interested in whether this variation could plausibly be modeled by a random walk around the drift. And so a starting point is to take our random walk model, simulate from it, and see if we get things that look remotely like the data. Let's take a Gaussian random walk with drift, where the drift and the variance are taken from matching the data. Here you see mu and sigma come from the data. And then X1 and X2 are just two independent simulations, and we can plot them. I think particularly simulation X1 looks not so different from the kind of things that the data are doing here. Simulation X2 suggests that according to this model, you could have even more extreme deviation from linear trend than what we in fact observed. Okay, so these plots all seem reasonable as a defense of a random walk with drift model for the S&P 500. The next thing you might want to do to refine that investigation is plot the sample autocorrelation function of these differences to see if they look like white noise as the model predicts. Now, another little thing here on the top line, I have talked about diff log SP500 using computer code notation. I want to alert you here that when you're writing projects, it's better to write everything in math. In the end, that gives a more kind of concrete way of writing things down. So here I've, if this is, if this is 1 and this is 2, um, 2 is better than 1. For midterm projects. We're going to talk more about midterm projects in due course. But I just want to point out to you that the notes are not necessarily a perfect role model for your projects. The project ideally would be a little bit more formal than the notes. Okay, anyway, we can do this. We can plot the sample ACF, and we see, here it is, the all the autocorrelations at lags other than 1 are very small. Some of them peak outside this testing region given by the horizontal blue lines, but not very far. They're still very small. So this looks close to the ACF of white noise. There's some evidence for small non-zero autocorrelation at lags 0 and 1. Let's look again and see if we can see that. Yeah, if you look super closely, you can see what's going on there at lag 0 and 1. But here we have a very long time series. When you do have a long time series, statistically significant effects may be practically insignificant. And this difference between statistical significance and practical significance, that's something that sometimes comes up in intro stats classes, but let's review it in this time series context. Why may the length of the time series be relevant when considering practical versus statistical significance? And like all questions, you're welcome to pause the video and think about it before you get my answer. So I'm going to say, when the time series is long, even very small effects may be statistically significantly different from 0. Even if their magnitude is practically irrelevant. Okay, so it looks like the random walk with drift model for the S&P 500 has more or less passed that test. It's well modeled by white noise, by that diagnostic test. However, if you look at the absolute values of the centered returns, you get something that's a little more thought-provoking. Here's the ACF of the absolute value of the centered return, Z minus mean Z. And there's certainly autocorrelation here, right? And let's think about, to what extent does this plot refute the white noise model for centered returns, or equivalently the random walk model for the log index value? Well, have a think about that. So it's a subtle question, and it relates to what you think is the white noise model, right? When we defined the white noise model, we defined it in terms of uncorrelated processes, not independent processes. So let's say the general definition of white noise, which is weak stationarity. This permits correlation between absolute values. It says the raw epsilons are uncorrelated, but it doesn't guarantee that the absolute epsilons are uncorrelated. However, strongly stationary white noise, e.g. Gaussian white noise, this does require independence. And independence implies implying if two random variables are independent, then any function of them is independent. And this is refuted by this plot. So there you go. There's more subtlety to modeling the S&P 500 index than just a Gaussian white noise model. Okay, again, this is relevant if you're starting to think about midterm projects. Not bad for you and your group to start thinking what you will do. Some of you will be interested in finance, some of you will not be interested in finance. If you are interested in finance, then you should bear in mind that nowadays nobody is surprised that the sample ACF of a financial return time series shows little or no evidence for autocorrelation. Deviants from the efficient market hypothesis, if you can find them, are of interest. So if you can find a good way to predict the future of a stock index, of course that's good, but generally you can't. It remains a challenge to find good models for volatility, which is this conditional variance process of the financial returns. And so oftentimes that's a more practical and still interesting problem rather than trying to find a better predictor of the stock market. Well, I think that's it for chapter 3, folks. Bye for now.